I gave this series of lectures here in Roscoff in 2017. And well, I had no lecture notes ready, but they wanted to publish lecture notes, so I was forced to write some. So some are available now. And as Rajan said, yeah, well, I will give them to you, yeah. But what I would like also is to keep, yeah, trace of your name, yeah. So if you could just send me an email, yeah, to you saw the email address in red color, yeah. So that, well, I may easier identify you, and if we need to interact in the future, it will be nice. So this is my email address, yeah, jsurdej@ulg.ac.be, yeah. So it would be good if you just send me an email. Okay. So, well, in addition, yeah, to lecture notes, yeah. My wife Anna, yeah, is going to videotape, yeah, the lectures. So if later on, yeah, you forgot about something or would like to see once more a demonstration, well, it's very useful, yeah. We do that for all the lectures, yeah. I'm giving, and well, all the videotapes, yeah, are freely available, yeah, on internet, yeah. So this is very handy. Okay, so I will just start now here and just show you, well, preliminary table of contents, yeah. So first I will start with an introduction, general introduction, yeah, to let you know what will be the content, yeah, of these lectures. Then I will proceed with some reminders, yeah, that we need to understand, well, the theory, yeah, of interferometry. Well, brief history about the measurements of stellar diameters. You will see that, you know, many scientists, yeah, thought about, you know, how estimating the size of a star in the past, yeah. Then I will address, yeah, the problem of light coherence. Then just mention examples, yeah, of major interferometers, yeah, that you could perhaps one day use yourself, yeah. And then I will end up, yeah, with the three important theorems and some applications to give you a better and deeper insight, yeah, in the theory of interferometry. So I will just start with the introduction. You know, very often, yeah, people ask, well, would it be possible to have a look at the star with a telescope, yeah? And then we show them, yeah, a star, and they say, well, show me another one, and well, it still looks about the same, yeah? No difference. And indeed, if we would be above the Earth's atmosphere, and we would look, yeah, with a telescope having a diameter d1, a very distant star, what we would see in the focal plane of the telescope, yeah, is just a dot of light, yeah? A dot of light which doesn't contain any information about the size, the shape, the temperature, the luminosity of the star, neither about its distance, yeah? All stars look the same. It's just an airy disk, yeah? So it's a, well, pattern of light diffraction, yeah? And what we know is that the angular diameter, yeah, between the two first minima, so you see here a dark fringe, yeah, is 2.44 times the wavelength divided by the diameter, yeah? So this is expressed in radians. So if you work at shorter wavelengths, well, the dot gets smaller, which is good because the angular resolution of your instrument improves. Or if you would increase the diameter, well, it would be better. And this is what is illustrated on the next slide, yeah? Now, we have a telescope with a diameter d2, which is bigger, larger than d1. And what you see is that, well, the size of the central dot of light, yeah, is smaller, yeah? So it's better. The angular resolution improves, yeah? So by increasing either the diameter of the telescope or working at shorter wavelengths, yeah, you improve the angular resolution of your telescope. And therefore, we have a space telescope, yeah, above the Earth's atmosphere, yeah, the HST, because, well, it can work, well, down to ultraviolet wavelengths, yeah, so very short wavelengths. And the diameter, well, it's quite important, 2.4 meter. Okay, so, well, astronomers have always dreamt about constructing bigger and bigger telescopes, yeah? But still there is a limit, yeah? Well, from a technological point of view, in the maximum size that you could construct a telescope, and nowadays, yeah, the technology doesn't allow you to go far beyond 40 meters, yeah? So you have the ELT project, you have the TMT project, you have the GMT project, yeah? Okay. So this is very unfortunate. Okay, now, let's assume we are looking now at an extended object, yeah? Well, a kind of a Earth-like planet, yeah? Well, it's very clear, yeah, that by using a telescope with a larger size, yeah, you would see more details, yeah, on the extended object, yeah? Because in fact, this image would just be the convolution product, yeah, of the point spread function by the real image of the object you are looking at. I'll come back to that, in more details later. Well, fortunately, yeah, in 1868, Fizeau and Stefan, yeah, proposed, or they just realized that in terms of angular resolution, two small apertures, yeah, separated by a distance of b, so this is a baseline, yeah, well, are equivalent to a single large aperture of diameter b, yeah, and this is fantastic, yeah, yeah, that they realized it, yeah. So it means that if you would separate these two telescopes by a distance of 400 meters, you could recover, yeah, along that direction an angular resolution that would be equivalent to that of a single dish telescope, yeah, having a size of 400 meters. Yeah? And for 400 meters is typically the baseline achieved by the Schara array in Mount Wilson. And well, VLTI, yeah, goes up to about 200 meter baseline. Now, instead of observing, yeah, an airy disk, yeah, in the focal plane of such an interferometer, what you would see is still an airy disk, yeah, still an airy disk, but crossed, yeah, by interference fringes, which are alternately, yeah, bright and dark, bright and dark, bright and dark. And now the interfringe, so the separation between two bright fringes, yeah, is just about equal to lambda over b, where b is a baseline, yeah, between that separates the two telescopes. So these are very positive news, of course. Okay, now let's have a look, yeah. If you observe, yeah, an extended object, yeah, with a small size telescope, this is what you would see, yeah, from a very distant Earth-like planet. By increasing the size, well, let's go to TMT. Well, it would already be improved, but if you would be using, yeah, well, an interferometer with still a baseline 10 times larger, you would see 10 times more details, yeah, along the line joining the two, yeah, single pupils. What you see exactly when using a telescope or an interferometer, yeah, as I said before, and we will see it in more details during the lecture, yeah, this is just an introduction, yeah, is a product of convolution of the point spread function. So the point spread function is the image you would see with that instrument of a very distant point-like star, convolved with a real image of the source, yeah. So I may write it like that. That the distribution in intensity is a function of the angular coordinates. These are the angular coordinates in the sky, yeah? Zeta and eta. Is just equal, yeah, to the convolution product of the PSF. So point spread function, what you would see, yeah, if the object is point-like, a star. This is a convolution product, yeah, times, well, the ideal, yeah, distribution of light of the extended object you are looking at. And this you don't know, of course. You only observe this, yeah. Now, as you know, if you take the Fourier transform, yeah, of the left-hand quantity, it would be equal to the Fourier transform of the right one. And you would find that the Fourier transform of the intensity is equal to the Fourier transform of the PSF times, this is a natural product, the Fourier transform the real intensity. And now you'd say, well, the quantity I would like to recover is that one, yeah? So how to do? Well, it's easy. You divide this quantity by this one, PSF, like this. And you find that Fourier transform of what you're looking at, of what you're searching for, yeah, is equal to the quotient, yeah, of those two quantities. Now, what you would do, you would take the inverse Fourier transform of this would be equal to the inverse Fourier transform of that. And now this would give you exactly the quantity you're interested in, yeah? So this equation, yeah, seems to show you that in principle you could recover, yeah, the real intensity distribution of the object, of the extended object, yeah, by taking the inverse Fourier transform of the Fourier transform of your observation divided by the Fourier transform of the PSF, yeah? And this would work, yeah, if you would have a very good coverage of the UV plane in space frequencies, yeah? But usually, this is very difficult to achieve, yeah? So, if the Fourier space, yeah, is only sparsely covered, so you will have a few data points, then what you would do, you would use a model. And while adopting, yeah, a priori a model, you're looking at an object and you suspect that it is a binary star. So you would say, okay, I know that I have 2 point-like components separated by a given distance and a certain orientation. And still, probably, you would be able to recover, yeah, what is a real angular separation between the 2 stars and what is the flux ratio between the 2 stars, yeah? So, okay. So this is just an introduction, yeah, to show you what we will cover during these lectures, yeah, and I will go into more details and we will understand exactly, yeah, how to derive those quantities. Okay. So now I will start with some reminders. First, concerning the representation of the electromagnetic wave, and after we'll go to the principle of Huygens-Fresnel. As most of you know, yeah, when we are looking at objects in the sky, well, most of these are not resolved, yeah, with the exception of the moon, of the sun, yeah. But even Jupiter, Venus, yeah, we cannot resolve them with our eye, yeah. And so the subject of the lecture today is something like that, yeah. Let's assume that you are looking, yeah, at the bulb of light, yeah, a very thin filament, yeah. And you're very, very far away, yeah? So let's say 10 meters, yeah? Would you be able, yeah, to estimate the linear diameter of the filament of the bulb? We'd say no. Well, after the pause, yeah, so in about an hour from now, you'll see we will construct, yeah, well, each of us, yeah, a small interferometer that would enable you to find what is the linear diameter of the bulb of the light, yeah? So, well, we have here some aluminum paper, some needles, etc. And we will construct a small interferometer that will enable you to estimate, yeah, what is the thickness, yeah, of the bulb of light, yeah? So, let's assume you are outside and you see a bulb of light, yeah, at the distance of 10 meters. You could use that instrument, look at it, and find what is the linear diameter. It's a micro or milli interferometer, yeah? Now, astronomers do the same with the stars, yeah? So they are observing a very, very distant stars with interferometers. And now here I have represented, yeah, the linear diameter, 2 times the radius, yeah, of course, yeah? Now, delta, big delta, is twice the angular radius. Now, what is the angular radius? Well, the angular radius, or I would say the tangent of the angular radius, yeah, is equal to the linear radius of the star divided by its distance, yeah, z. Okay, this is easy. Now, there is a nice relation, yeah, between the flux, small f, that you observe from a distant star and the flux at the surface of the star. So, how to derive the relation? Well, the luminosity of a star, yeah, is equal to the surface, yeah, of the star, yeah, which is assumed to be a sphere, multiplied by its intrinsic flux. Yeah. Now, conservation, yeah, of the flux, you can also say, well, at a distance z, the sphere, yeah, is much larger, yeah, and if I multiply it by the apparent flux observed on Earth, yeah, I still have this equality. So z is the distance between the observer, yeah, and the star. F is the apparent flux. This is the flux at the surface of the star, and this is the radius of the star. Yeah? So from this relation, you see that if I divide r over z square, this is equal to small f divided by big F square. But r over z, this is the angular radius. Yeah? So this is equal to rho square. And from this relation, yeah, I may just infer that where the absolute flux, yeah, of the star is equal to the apparent flux. There is no square here. Yeah, sure, absolutely. Yeah. So F, big F is equal to small f, yeah, times 1 over rho square. Correct? Yep. So you see that by if you know, yeah, what is the angular radius of a star, measuring its apparent flux on Earth, you may estimate, yeah, what is the stellar flux, yeah? So the flux at the surface of the star. Now, if you make use, yeah, of the Stefan Boltzmann law, yeah, you know that so the absolute flux of the star is proportional, yeah, to the power number 4 of the effective temperature. So which means that the effective temperature of a star is equal to the flux divided by the constant of Stefan Boltzmann, yeah, at the power 1 over 4. And now if you make use of the flux here, you find that it is equal to small f over sigma. This is at the power 1/4 and divided now by 1 over the square root of rho. Correct? I hope. Well, I'm not sure, but about this one, are you? Do you find the same result or not? It's okay. Yeah. If you say it's okay, it must be okay. Yeah. Okay. So what is fantastic, yeah, is that by just measuring the angular radius of a star, yeah, you may get an estimate of its effective temperature. Yeah. And this has been a major use, yeah, of stellar interferometry to provide, yeah, reliable estimates of the effective temperature of stars, yeah, which enter, you know, when you make stellar evolution calculations, yeah, and model atmospheres. Yeah. I come to speak about a beam of light radiation. Yeah. So a beam of light radiation can be assimilated, yeah, to the propagation of a multitude, yeah, of electromagnetic waves, yeah, with velocity of 300,000 kilometers per second. Yeah. Well, in the vacuum, of course. Yeah. And now, well, this is a representation, yeah, of the electric field. Well, assuming that the wave, yeah, is a plane, is linearly polarized, yeah, that its frequency is nu, the wavelength lambda, yeah, and if I represent, yeah, the propagation of the electric field, yeah, as a function of time or as a function, yeah, of the distance along one direction, represented by the abscissa z, this is, yeah, a nice representation, yeah, of how it varies, yeah. So lambda is a wavelength, yeah, nu is a frequency, and big T is a period. So now we visualize, yeah, the propagation of this wave, either as a function of time or as a function of the z-axis. Yeah? Let's assume that we freeze the time. So t equals 0. Yeah? So it would be the propagation as a function of z. Yeah? and the separation between two crests, yeah, would be equal, of course, to the wavelengths, yeah, to the wavelengths of the light. Now, you could consider that we stay at the same spot, yeah, along the z-axis, for instance, z equals 0, yeah, and look how the waves vary as a function of time. Now, the separation, yeah, between two crests, yeah, will be the period, yeah, t, equal 1 over nu. Now, by multiplying, of course, t by c, the velocity of light, this is equivalent to the wavelengths, yeah? Okay, now, so it's very convenient, yeah, to represent, yeah, this expression, yeah, in the complex form, yeah, as follows. Well, the electric field, yeah, is represented by the real part, yeah, of the product of the real amplitude, A, so this is a real quantity, multiplied by the complex exponential function, yeah, which is the following one. Well, why it's very convenient is because what we will do, we will drop, yeah, the real part, then we will essentially, well, operate linear transformation on the electric field, and just after, at the end of your calculations, yeah, you would take the real part of the result, yeah, and would find what you're searching for. Now, the fact that it is very convenient is due to the fact that you can represent, yeah, this complex exponentiation, yeah, as the product of two quantities, one which essentially depends on the time variable and one which depends on the space variable. Yeah. Okay, so it is shown here. So I abandon, yeah, the real part, yeah. So then we make a linear operation, and at the end we will take again, yeah, the real part, but let's forget it for the moment. So this is a part which depends on the time variable, and now this is the part which depends on the space variable, yeah, where phi is equal to 2 pi times z over lambda, yeah. And now this, the product of these two quantities, yeah, we will represent it as being the complex amplitude, yeah, of the electric field. So the previous expression is represented as follows, and this is the complex amplitude, yeah, of the electromagnetic field. So I will use it later on, and so should just write it down on the blackboard so that we don't forget it. So the electric field can be represented as a product of the complex amplitude, yeah, A times I2 pi nu t. So A equals the product of the real amplitude times with phi equal to 2 pi z over lambda. Now, unfortunately, yeah, unlike when you are observing the radio, yeah, it is impossible, yeah, to measure the variation of the electric field, yeah, as a function of time, yeah, because, well, the frequency is much too high, yeah. Well, typically the wavelengths, visible wavelengths, 5,000 angstrom, yeah, the frequency, yeah, of the electric field, yeah, is something like 6 times 10 to the power 14 hertz, yeah. So it's much too fast, yeah. So if you'd like to get the next Nobel Prize, yeah, try to find an instrument that is capable of measuring, yeah, the variation of the amplitude with such a frequency, yeah. Okay, so the only thing you can measure, yeah, is the intensity, yeah, and the intensity is the time average of the energy, yeah, passing through a surface element per unit of time per solid angle, yeah, and placed perpendicularly, yeah, to the propagation of the beam. So it's given, yeah, so the intensity is proportional to the temporal average of the square of the electric field, so it's given by that expression. And if you replace, yeah, the quantity E by what we had before, well, I could say, okay, E equal A times cosine of 2 pi nu t. what you would find is that the intensity is equal to 1 over 2t times integration from minus t to plus t of. So the square of this quantity would give you a square times cos square 2 pi nu t dt. Okay, now, well, you can make use of the following relation, yeah? Cos of 2x equal 2 times cos square x minus 1, yeah? So you would find that this is equal to a square over 2t multiplied by minus t at t of, I will extract it from here, so it would be 1 plus the cosine of 4 pi nu t divided by 2 times dt. Now, when you will integrate this quantity, cosine, you will find a sine, yeah, but which will vary over well, many periods of time, yeah, which means that its contribution will be equal to 0, and what will remain is just a square over 2t divided by 2. And then if you integrate 1 between minus t and plus t, you will get 2t here. So the 2t disappear, and you find that it's equal to a square divided by 2. So this is interesting. We find that the intensity, well, is proportional to the square of the real amplitude, yeah? And by convention, yeah, well, astronomers are defining the intensity of the electric field, yeah, as being just equal to the square of the real amplitude, yeah? Which is also, yeah, the square, yeah, of the module of the complex amplitude, yeah? And which is also equal, of course, to the complex amplitude times its conjugate complex, yeah? So these are just reminders, yeah, just reminders, which will be important here for the remainder of the lecture. Now I come to the principle of Huygens-Fresnel, but before going there, is there any question? I mean here, that's all of that is still clear, yeah? So let's go now to the principle of Huygens-Fresnel, yeah? So following Huygens, yeah, the propagation, yeah, of a wavefront, yeah, can be assimilated, yeah, to, well, if you take any part, yeah, of a wavefront, yeah, it is as if, yeah, it was, it could be considered as emitting, yeah, a wavelet, yeah, secondary wavelet, and so you take all the points, yeah, along these wavefronts. After a certain time t, yeah, you look where are the wavelets, and now you take the wavefronts, yeah, of all those wavelets. And what you find is that, well, the propagation of this plane wave after a certain time is still a plane wave. Yeah? You can do the same for spherical waves. So here is a spherical wave at the time t. So you consider different points of the spherical waves. Now, wavelets, yeah, are being emitted, yeah, by all these points, and after a time delta t, you take the wavefronts of all the secondary wavelets, and what you find is that, wow, it's still spherical waves, yeah? You just have to consider a very large number of secondary points, yeah? And so this is a principle of Huygens, and Fresnel added the fact that you should, yeah, also consider the interference between the wavelets. So if two wavelets, yeah, oscillate and touch each other or in phase, yeah, then their amplitude will just be cohered, yeah. If they are in, well, opposite, if they are also oscillating in opposition, yeah, then the resulting amplitude will be 0, yeah. And by just so adding, you know, this interference between the wavelets to the construction principle of Huygens, yeah, well, Fresnel has been able, yeah, to account for the diffraction effects, yeah, caused by optical light, yeah. For instance, if you take the objective, yeah, of a telescope and let a wavefront, yeah, plane a wavefront, yeah, falling onto it, yeah, well, the wavefront tends to go around this obstacle, yeah, and then the wavelets are interfering, and the result is that at the focal plane, what you're observing, yeah, is not a dot of light, yeah, but it is an airy disk, yeah, airy disk due to the interference. So, of course, we consider here that we are working with monochromatic light, yeah. So you see that during these lectures, we will have the tools, we will develop the tools, yeah, to estimate exactly, yeah, what is the size of the airy disk and what is the expression, yeah, which may account for its light distribution. Now, well, this is interesting for the experiment that we shall do in a moment, yeah. The angular resolution of our eye, yeah, is given still by the same expression, yeah, 2.44 lambda over d, where d is the diameter of our pupil, yeah, and where typically our pupil, yeah, have a dimension that may vary between 1 and 5 millimeters, yeah. If you make the calculation, transform the radians in second of arc, you would find that when your eye, yeah, has a size of about 1 millimeter, its angular resolution is about equivalent to 2 arc minutes, yeah. And when it's widely open, yeah, so up to 5 millimeters, yeah, well, it's 5 times better, yeah. So it would be, well, 2 minutes of arc divided by 5, yeah. Okay, so this gives you an idea. Okay, now when you're using a small telescope, yeah, 1 centimeter, typically, a telescope, well, the diameter of the airy disk, yeah, is something about 15 seconds of arc. Now, if you increase the size of your telescope up to 15 centimeter, it will be 15 times smaller, yeah, so about 1 second of arc, yeah. And what is very unfortunate, yeah, well, under our skies, is that if we still increase the size, the diameter of the telescope, yeah, the angular resolution doesn't improve anymore, yeah. We are, well, our angular resolution is limited, yeah, by the agitation, yeah, in the atmosphere. So what happens is that there is typically at a height, yeah, between 5-10 kilometers, yeah, we have a regime of eddies, yeah, and well, this is the atmosphere, and typically the size of these cells, yeah, may vary between a few centimeters up to 20 centimeters under the best conditions. And so, well, in the focal plane of the telescope, yeah, well, it is as if, yeah, well, the only part of the mirror which are coherent, yeah, are of a size of about 20 centimeters or down to 2 centimeters, yeah, depending on the condition in the atmospheric layers, yeah. Now, if you take a monochromatic light, so if you observe with an interference filters, yeah, what will happen is that light passing here and light passing there could interfere, yeah, and either interfere positively or destructively. And what you would observe in the focal plane, yeah, is just a series of granules, yeah, called speckles, yeah. And still, the individual speckles will have an angular size given by 2.44 lambda over d, yeah. But if the size of your telescope is too big, you have so many speckles, yeah, that it looks like, you know, a very, a very disturbing spot of light, which angular size is typically several seconds of arc, or under the best conditions, yeah, 1 second of arc or half a second of arc. That's all, yeah. So this is very unfortunate, yeah, for, well, amateur astronomers, that beyond 15 centimeter, you don't gain any more in angular resolution, yeah, because of the atmosphere. Well, at Devastal, yeah, last year, yeah, we could take some images, yeah, where the size of the point spread function was about half a second of arc, yeah. So it's a very promising site, yeah. Okay, now I come to the brief history about the measurement of stellar diameters, yeah? And everything starts with Galilei, yeah, 1632. So the way he proceeds is as follows. He tries to get an estimate of a bright star. Well, let's assume that it is Vega, star of magnitude 0 in the sky. So what he did, he just took, well, a very thin wire, and he let it hang, and then he put his eye behind, looking at Vega. Then, of course, if you are too far away, what happens is that you see the star, but then you get closer to the wire, and well, from a minimum distance, the star gets occulted. And now his estimate of the angular radius of Vega was the angular radius of the wire. So let's assume that the linear diameter of the wire is d, and the distance between the eye of Galileo to the wire is z, where the angular diameter of the wire would be d over z. And this would be twice the angular radius of the star. And so he found, proceeding that way, that the angular diameter of star is probably around 5 seconds of arc. It's 5 seconds of arc. And this was already a kind of revolution, because before Galileo, people thought that the angular diameter of the star was about 2 arc minutes. Now, could I ask you, why 2 arc minutes? Why people thought that the angular diameter of the star was about 2 arc minutes? No? 2 arc minutes? Resolution of the eye. Resolution of the eye. Now, if I come to the next question, why Galileo estimated the angular diameter of the star to be 5 seconds of arc? So you're right. That was because of the thing when he was observing. If the thing would have been, thank you, 5 times better, he would have estimated that probably the angular diameter of the star is about 1 second of arc. So he was victim of the atmospheric thing effects. Now the next one is Newton. Newton. And well, Newton did that in a very, very clever way. Really fantastic. Well, he proceeded as follows. Well, the sun is visual magnitude. Well, he didn't know exactly that it was minus 26.7 at that time, but the visual magnitude of the sun is minus 26.7, right? So it's very bright. And he said, well, let's assume that Vega is a star like the sun. So this was a very good, vision. In that I take the sun and put it farther and farther and farther away until its apparent magnitude gets equal to 0. Well, its angular diameter would shrink to a size which would be, well, the typical angular diameter of a star like Vega. So the way he proceeded is as follows. Well, you know the relation, according to which, well, the apparent magnitude of the sun minus the apparent magnitude it would have if it was set at the distance of Vega, but Vega is an apparent magnitude of 0. So I would say minus 0. Well, it's equal to minus 2.5 times the logarithm in a base 10 of the flux of the sun as we observe on Earth, right? Divided by, well, the flux of the sun, if it was at the distance of Vega, correct? Okay. Now, I may revise this relation as follows. Okay, the flux of the sun, as seen from the Earth, well, is just equal to the luminosity of the sun divided by 4 pi z square, where z square, is the distance between the observer and the sun. Now, divided by the flux the sun would have if it was at the distance of Vega. So, well, this is also the luminosity of the sun divided by 4 pi. And here I would say, okay, the distance of the sun if it was placed at the position of Vega. Okay? Now the nice thing here is that the luminosity of the sun here and luminosity of the sun here goes away. Yeah? 4 pi and 4 pi goes away. And now what I do, yeah, I will just insert, yeah, the square of the radius of the sun above and below. So in the denominator and in the numerator, yeah. So here I put r square sun, r square sun. Now what we obtain is that it's minus 2.5 times the logarithm of. Okay, can you tell me what that is? Yeah. So it's the quotient of the radius of the sun by the distance of the sun. It's the angular radius, yeah, of the sun as seen from Earth. Okay, but so I just write here rho sun square. And now if you do the inverse, yeah, this divided by that, yeah. Well, here I forgot the square, yeah. Yeah, so this is what? This is the angular radius of the sun if it was as a distance of Vega, yeah. So I could say, okay, like this, yeah. And from this relation, yeah, I find that, so here, this quantity minus 0, so it's minus 26.7 minus 0. So the minus and minus goes away. And I find that from this relation, that 26.7 divided by 2.5, here I put 10 to the power of this quantity, is equal to the radius of the sun square divided by the radius of Vega square. And finally, we find that the angular radius of Vega is equal to the angular radius of the sun times 10 to the minus 26.7 divided by 2.5, and then I should still take a square root, so divided by 5, like that, okay? And if you do that calculation, yeah, so we know that this is half a degree, 30 arc minutes, yeah? And if you make the calculation, yeah, well, Newton found that the angular radius of the sun, if it was placed at the distance of Vega, should be about 8 milliarcsecond, yeah? So he was the first, yeah, to get a good estimate of an angular radius of a star, yeah? Yeah, and it's very nice, yeah, deduction. Now, if you would take, of course, the real apparent magnitude of the sun that we know today, well, we would find that the value, oh no, so he estimated 2 milliarcsecond, rather than with the correct value of the apparent magnitude of the sun, we would find today that it is 8 milliarcsecond. But still, yeah, today we know by measurement, interferometric measurements, that the real diameter of Vega, yeah, is 3 milliarcsecond, yeah. So he had a very good estimate, yeah, of what the angular radius of a star should be.